Okay, welcome everybody. Thanks for coming. I'm glad you're here. Do you have any questions administratively about the course at this point? No? Okay, we've kind of hit probably a pretty consistent feel, right? There's a lab, there's a post-lab, there's being here, there's being there. Things are going to change just a little bit in the next couple weeks. We'll start also adding the dynamic of the group projects. So I'll talk about it here, and there will be some information that we'll share over Canvas in terms of how to start getting your groups together. They will be of 3 people, and it will be an opportunity to start to brainstorm what you want to do, the project you want to pursue. Okay. There is another change. We're going to try something a little bit different. Not that different, but a little bit different with the attendance. So what's going to happen is, and you can do this now, I just want you to create in your SharePoint folder a new subfolder called class attendance. So what's going to happen there is there will be, at some point in the class, right, we'll have a code that you'll put into the Canvas bit, but you'll also just upload a selfie with that image in it to SharePoint. Okay? And of course, that will be dated. You'll have a time right on SharePoint, and then you'll also get the credit. You'll get the credit instantaneously. Okay, so that might make people feel a little bit happier as long as you put the code in, and then we can verify in your SharePoint folder, if you weren't back here. Any questions on that? How that's going to work? Yes.
So, for example, if I take a picture of my phone, if I wait and then upload it, is it at night, or do I have to upload it in class?
This is a very good question. So this is an experiment. You should be able to access that SharePoint folder from a web browser on your phone. All right? So I'm asking you to go ahead and try to do that now at the beginning of class. If it doesn't work out this time, we'll have to figure something else. Okay? But if you could go ahead and make sure you can access your SharePoint folder, create that subdirectory, that subfolder called class attendance in your folder, that'd be great. So that way, when you take a photo, you can just upload it there. Yes.
So just to clarify, just like the one for the folder that we actually make, that's where we put the selfie and then we can put it into Canvas.
Right. Correct. Thank you for the clarifying question. And that class attendance folder will just keep building over the course of the rest of the semester. It's a little bit different, yes.
You want us to make the folder in the same place where we see all the labs?
Correct. So you're saving me from having to go into everyone's folder and create a new subfolder called class attendance. And yes.
Does the picture still need to be like on the screen?
Oh yes. In fact, so the TA, one of the TAs has let me know that they would very much appreciate being able to see the image in the slide, because there's some confusion that maybe certain things are not happening as they should be. Okay, so the priority, have a part of your face in it, and I've got it in huge letters or huge font now. Okay, what's supposed to be on that slide, so that the TAs can actually identify what you're taking a picture of. Any other questions on that? Okay, and I don't know. I don't want to be mean, but maybe we'll do the attendance a little bit earlier today. Okay, and so, well, actually, I won't, because that would be mean. Okay, but let's just as a forewarning. Okay, it doesn't always have to be at the end of the class. Okay. All right. Okay, so that's the administrative stuff. Let's get going. Today is going to be hopefully not too dry, because we'll have some conversation. You'll enjoy looking at differential equations, partial differential equations, But if it is a little bit dry, please forgive me. What we're going to attempt to do is transition from molecular dynamics to heat transfer. Okay? And might not just be from molecular dynamics to heat transfer that we're trying to make this move, okay? But also, by the way, does everyone know that there are blank slides available on Canvas at this point? Okay, so I'm trying to give you the blank slides, and if you want, you can just fill in with my writing. Okay, maybe that wasn't clear, but anyway. So you don't have to copy, and then I upload, with errors sometimes, the slides from class to Canvas. So you've got everything, right? Okay, anyway, so here we might like to model everything with particles, but there are some difficulties with that. One, to represent a very large structure, or even a very small structure, or medium-sized structure, you start to see that you need lots and lots of particles. And when you start thinking, oh, every particle interacts with every other particle through a unique base pair potential, you can quickly see that you're going to get a huge number of calculations that may not be the most efficient use of your time for computation. The other thing that can happen is these molecular dynamic parameters, or these potentials, like the Leonard-Jones potential with an epsilon and a sigma, epsilon being the depth of that well, sigma being the zero potential, the distance to the zero potential. Those might be difficult to relate to real-world properties. So how do you relate these properties to the elastic modulus? Or today, more relevant, how do you relate them to thermal conductivity, or thermal diffusivity, or specific heat, or density? So all these parameters in molecular dynamics can be difficult to fit to stuff that, well, we care about on a more regular daily basis. And so this is an opportunity to introduce a new physics. Up to this point, we've been doing particle dynamics, and we've been happy with the Rayleigh velocity method or some form of modified Euler method. But today, we're going to go beyond discretizing time and discretize space as well. Okay? And so essentially, we're saying, let's create a grid. Let's create a grid. And we're going to end up looking at now, as we step through time, what's happening at the nodes on that grid, or the vertices on that grid. So physically, though, there is a way for us to relate what's happening at a molecular level or an atomic level to what we're trying to model in, say, heat transfer. We can begin to think of these particles being organized, them vibrating, them moving, and thinking about, okay, how far do they really travel? How far does a packet of heat really travel? And if it's more excited, it can travel a mean free distance that would be larger. Okay? And it can do that in a less shorter period of time. So we can begin to leverage what we've described with the particle dynamics and start to make that something that you could kind of put on a grid and think about these particles behind the scenes moving between different positions on the grid. Now, you don't have to read all this, but we're pretty much going to be focusing on thermal conduction. Today and next week, thermal conduction. Today we're going to be thinking about how to use the finite difference method for this type of modeling. And then next week, we will begin to think about the finite element and get to think about ANSYS and its implementation of the finite element method to solve the same exact problem that we're going to solve today, okay? Or that we'll solve in the labs. So, yeah, you know, your MATLAB skills are now, you know, hopefully doing okay. And I think that this problem that you get to do, I tried the post lab for the post lab number 3 with the potentials and the colliding electrons or colliding atoms. The lab was colliding the electrons, the post lab is colliding atoms. I hope that with a little bit of reworking of the writing of the problem, it's not as bad as it used to be. Okay, that's my hope. Okay, but that's probably the hardest MATLAB that you get to do. Today's MATLAB hopefully will be a little bit not so bad. Okay. And also, of course, you have the template for you to work with. So we're going to be modeling thermal conduction. Okay, so let's start off by, here we go. By kind of drawing a box. And in that box, we'll have lots of heat packets that will move around. And if you open up Incorpore de Witt, the heat transfer textbook that some of you might be familiar with, or not, you would see a diagram that kind of looks like this in the first chapter of that book. Okay? I'm not being very careful here. I probably could, yeah, I don't know. It's not as random as a computer could make, okay? I have some bias, I guess. Like these 3 particles, what's the probability of those heat packets all moving in the same direction, right? Anyway, so these are particles that are in a space, and we're saying they're in a solid. And they are akin to the particles that we've been thinking about, but each one of these is some type of packet of heat. Okay, so it could be some type of phonon, some type of photon, some type of realistic or not realistic thought of what a packet of heat looks like. And it can kind of choose to move around. Now, let's say that this is the positive x direction, downward. Okay? And let's say that at this border, at the top, you have some form of heat up there. Okay, temperature, sorry. You have some form of temperature. And on this, okay, you have something that kind of looks like that at the bottom. And let's say that there's some, there's a difference in the temperature between these two sides. And then let's say that you draw a line through the system at some x value. Okay, this would be whatever. This is the distance x, right? So we've already got. We can, if we want, we can say, okay, this is our distance x to that point. We, based on this problem, can begin to think about what the average or the net flux of these packets would be through that cross section. Okay. So you can begin to say, oh, well, if T2 is really hot and T1 is really cold, the net flux of heat particles would be upward, right? It would go from the bottom to the top. If T1 were very hot and T2 is very cold, then the net flux would be downward and in the positive x direction. Okay? So we describe this flux. So there's a heat flux that we can describe in terms of Q. And if you look in different heat transfer books, like in comparative lit, they'll use like a Q dot dot to distinguish this Q from just a power of heat, a heat power. Okay, and so here the units are power per area, okay, or watts per meter squared would be one fair representation. And what essentially we're saying is that there is some type of value of the material. So how fast it allows the packets to move of heat, all right? And that we give by thermal conductivity. And then there is a derivative of, okay, and this is in 1D, so that's in the x direction. And there's a derivative of the temperature with respect to x. So let's take this example, all right, where we'll try. If T2 is high relative to T1, all right, then I could say, all right, and it doesn't have to be, okay? And I'm trying to figure out what's happening. My heat flux is going to be negative. Okay, it's going to be going in the direction opposite of this, right? So in that case, I would have a Q, and we keep the negative K there. And for it to be negative, I have this term here. My delta is the T2 minus the T1 over delta X, and then I have an I hat direction. And I guess I could say, we should probably say that our delta X could maybe be given as such. Okay? And if T1 is greater than T2, right, then this goes in the opposite direction, and it would be in the positive. Okay? Minus, minus. Now, this equation has a name. This is Fourier's law. Okay. And you've probably seen this, right? In one of your classes? Yes? Which class did you see then, Josh?
Heat transfer. I'm taking it tomorrow.
Okay, heat transfer. Okay, good. Have you seen it outside of heat transfer? Okay, so if you're an aerospace engineer, you may not, you can opt to take one of your technical electives, heat transfer. That might help you some in life, but that's fine. Okay, so you haven't seen it before. It's not necessary. Now you've seen it. Okay. And so we've got this way of describing heat flux, right? And the K, you can do the dimensional analysis on the dimensions, or on, you've got temperature, which is in kelvins or Celsius or Fahrenheit, but for our class we'll mostly deal with Kelvin and Celsius. And so the units of thermal conductivity are often given this way. okay, watts per meter Kelvin, right? And we have, I guess we could say this is thermal conductivity. Okay. And we've now simply tried to relate what we've been doing in molecular or particle dynamics to heat transfer. And we're going to now, instead of running our dynamic simulations on individual particles, we're going to run our simulations on differential equations. Okay? And you can already kind of see, oh, I've got some distances that for now and for in general with the finite difference method, they're all the same. Okay, so when we start doing finite element and finite volume, we can have different sized elements and thus different lengths involved. But for now and for our treatment of finite difference, the grids are all squares. They're all composed of squares, all with the same lengths. Okay, so in 1D, we've written now our Fourier's law. Okay, and it's right underneath there. But this one, as we've said, it's just a Q, and it's minus K, and it's dt dx in an I direction. Okay. We've gone through thermal conductivity. In 3 dimensions, the Q, or the heat flux, okay, is given by a very similar looking equation. But instead of a definite derivative, we're going to use partial derivatives to describe the behavior. And what do we see? This expression is the gradient of temperature. So it's like, oh, that silly negative of the gradient of the potential function. This is not necessarily, I mean, this is kind of like that. Okay, you can kind of see, oh, if I have a field of temperature, right, which you could kind of liken to some type of potential, I take a negative gradient of it, I can figure out what the motion of heat is in that system. And you may say, well, what motion? What are you talking about? Well, remember, watts are joules. Yes. Oh, okay, sorry. Yes, Kevin.
Why is K negative?
Okay, because, well, K is a positive number, okay, in terms of thermal conductivity, but the reason is so that if the lower quantity, or if the, not lower, but if the, what we'll call the 1, the upper, right, so less XE, okay, value minus the more XE value, right? Well, sorry. The more XE value minus the less XE value, okay, times K would give us the opposite direction, would give us flow in the opposite direction, okay? And so the negative there allows us to have the flow in the direction that's appropriate to the, well, to the changes that we're calculating. Okay. Does that make sense? So it's not that the K's are negative, it's that that's what Fourier's law dictates. So another way to look at this is to say, oh, this is really, I mean, if I say, okay, this is x2, this is x1, and x0, okay? What we're saying here, and this is just take this with a grain of salt, okay, is that the Q, all right, at x1 is going to be equal to the T2 at x2 minus T1 at x1, okay? And this would be over 2 delta x. Okay? That might be another way to hopefully make it make sense. Okay? The T2 is, so like T2, I mean, I don't even have to write T2. I can just write that it's the T of x2. And it's the T of x1, right? So T2 is equal to and T1 blast, that's probably better. T0 is equal to T of x naught. Okay. Yeah, okay, that math I think works out now. Okay, so that's why there's a negative sign there. All right, so now let's begin to think a little bit about flux into and out of a square or a prism. Okay, so if we have and so we'll make it a little bit 3D-ish, okay, to illustrate this principle. If we have a small element, and there's some heat flux, I guess we can do, we'll just call it like that, coming in over a cross-sectional area, and we have also a temperature of this element, and we have a heat flux out of the element. Like this, we can begin to think of what is the change in energy of this element as a function of time. So energy we'll give by E, and of course this is essentially saying it's a power, right? So it's going to be in terms of watts. In thermodynamics, which you have and are taking, right, you can think of this as being some type of sum of the heat into the system and the mechanical work on the system. Okay? So in this case, there's no mechanical work, so that goes to 0. And now, if we like, we can think the change in energy as a function of time for this element. Yes, there's a heat flux there, right, the dq. But in terms of going back to your high school physics, you know that if I have a block of material and it has some specific heat, or it has a heat capacity for a large object, I can relate that heat capacity to a change in energy to figure out what a change in temperature is going to be. or I can use the heat capacity. Yeah, exactly, right? If I know how much energy I have that I'm dumping in, I can figure out what the change in temperature is going to be. Okay, so here on this very small element, what we say is it's the density times specific heat capacity times the change in temperature in this element times the area times the length. So area times length, that's volume, right? So this quantity right here is volume. And the volume times the heat capacity, right, is going to give us, and times the density, or the heat capacity there, it's going to give us this kind of opportunity to think about what the change in energy is with a change in temperature. The dq dt, this quantity right here, this is essentially the heat flux, okay? So, but times the cross-sectional area. So this dq dt, this big Q, this is going to be equal to the Q into the system minus the Q out of the system times the cross-sectional area, because we said that this is a heat flux. So heat flux times an area gives us heat, power. And so now we can equate this to this quantity, and we write out that rho c dt dx, okay, and we can get rid of the a and the dx, so let's do that. Okay, hold on. Oh, sorry, that was wrong. Yeah, the change in time. Okay, so rho c dt, and we have our ADX, so we can divide both sides by dx. Okay, so we're looking at this versus equal to this. All right, so this is going to be dt, and we have this quantity up here. Over dx. So this dx came around and divided this side. Okay. This allows us now to relate Fourier's law, okay, with a change in temperature of an element as a function of time. Okay. And this is what we call the 1D heat equation. Okay, so if we look at this diagram, and we look at this equation, we can see that in 1D, what we've got here when we substitute in, so this is going to be going back here, we've got this Q is equal to minus K dt dx. Okay, so we can say that Q is equal to minus K times the gradient, or in 1D we said, in 1D we said that the gradient, right, is just going to be equal to dt dx I hat. So we can say that this quantity right here, rho c dt is going to be equal to like this, which essentially says take the second derivative of temperature. Like so. Okay? And so that's what the 1D heat equation is. In 3D, okay, what you have instead are 3 partial second derivatives of the temperature. And you can relate, or we can relate that to the thermal conductivity, the density, and the specific heat, and the Laplacian of temperature. Okay. So this quantity right here is also well known, and this is known as alpha. Okay, and alpha is what we call thermal diffusivity. Okay, really poorly written. Okay, so what is thermal diffusivity? Well, you have this idea of what thermal conductivity is, right? I mean, thermal conductivity is given to us by Fourier's law, and that says, okay, if you have, you can come up with a heat flux based on a change in temperature. Thermal diffusivity gives you an idea of how fast a material is going to change its temperature in a gradient. So if I have a very high thermal diffusivity, I don't know if anyone has any ideas for materials that have well, what are some materials that have high thermal conductivities? Yes. Okay, yeah, so, and they're relative ones, right? They're different. Copper has a very high thermal conductivity. It also has a very high thermal diffusivity. And it turns out that often rho times C is about the same for a given class of materials. Doesn't, like as you pack density, as you pack mass, then the specific heat capacity goes down, right? Because that's per mass. Anyway, so thermal diffusivity is this term that kind of gives us an idea of how fast the temperature is going to change, whereas thermal conductivity is just based on, it just tells you what heat is. And of course, they're related to each other, right? So if you have a high thermal conductivity, you can have, there's a chance that you'll have high thermal diffusivity. Air, not usually very conductive, not a very high thermal diffusivity. But what do you have to be worried about when you're dealing with air and heat transfer? Yes.
Combustion?
Oh, okay. Yeah, maybe the air could combust under certain situations. Okay. All right. Yeah, that was not the answer I was looking for, but I like it. Okay. Yes. Yeah, convection, right? So you have to be concerned about how the air is moving, because then it can move the heat as it moves and as it circulates, right? So often what you'll see is insulation making use of air pockets, okay, but those those air pockets are keeping the air from flowing through it. So you go any building, your house, right? You're going to have something that's making sure that the air doesn't have free flow. Even though the materials that are kind of there to block the convection, they may have a lower thermal diffusivity than the air itself. They're porous. Okay. Let's continue. So here are some values for thermal diffusivity and thermal conductivity, or the inverse, thermal resistivity, okay? And so, like we were just talking about, air has a pretty low thermal conductivity. Copper has a high thermal conductivity. And then if you come over to this chart and look at different materials in this one, what you'll see is we love steel, and steel is it's cost effective for structures and whatnot. And I guess it gives us one more benefit if you don't want to leak a lot of heat out of a building or a structure, because it has a lower thermal diffusivity than, say, many of the other metals, like aluminum. Okay? Aluminum has a thermal diffusivity that's almost, it's about 10 times that of carbon steel. And then in this, you'll see that air, right, has a much lower thermal diffusivity than some of these other materials. Okay, so this is just a way to kind of get your head in the idea of, all right, do I expect very fast changes of temperature for small amounts of heat flux or small amounts of temperature difference, or is it going to take a little bit longer? Now, what do we think about in this class besides the physics? We think about the way to numerically solve these physical problems. And so we've introduced some differential or partial differential equations. And what we're going to talk about now is how we can use a numerical method to solve these equations. Now, unlike the three-body problem with particle dynamics, where there's like no closed form solution, in this case, there are closed form solutions for many of these problems, okay? The simple ones. But once you start adding more complexity to the geometry, you leave an element, you have even just like a cavity with walls and it's hollow in the middle, and you want to figure out what the temperature is in the middle, or maybe hollow is not a good example. Maybe you have different materials stacked. Actually, that's pretty solvable too, analytically. Because you can have the R values and you figure out what's going on. But as you have more complicated geometries, you're not going to find a simple closed form solution. So we're going to introduce simulation to do this. And the basic idea with the finite difference approach, which is now the method we're introducing, is that you and I will break up our object into a series of equally spaced, not that, that's, wow, I naturally got smaller in my gaps. But we have all these different points that we pick, and they have a gap between them that we'll call delta x, or our spacing. Okay. And if I'm at this location in the middle, I'll call it x sub I, And if I'm going up, all right, closer to the xn, I'll call it x of I plus 1. And if I go one before, that's x of I minus 1. Now, if we think about what a derivative is, we can say, well, it's some change over some change, or some, right? And we say, oh, wait, we're talking about delta t over delta x, right? And we more formally remember, which is a stretch, unless you're really in this field, the Taylor series expansion. We remember that we can approximate derivatives. And so if you're interested in a value f of x at some location, and I know the value at another location, so f of a is some type of constant, or f of a is a value that's known, but f of x is not known. And I know something about the slope, okay, of this value at another, the known at the known location, right? And I know something about the second derivative, okay? I or you, we can use this approximation, and we know something about the third derivative and fourth derivative, right? We can use this Taylor series expansion to approximate or to get very, very close to the actual value at a new f of x. And if you also remember, you kind of at some point said, you know, it's not really worth it to keep going and keep taking these other derivatives. I'm good. Like, remember, like, I'll just use like 2 terms even of this Taylor series approximation to get my value that I'm interested in. And you have probably this idea already in your head, well, this approximation is probably going to be more accurate with fewer terms if my distances are small. So if I break up and I discretize my object into lots of small little bits, and I have lots of little points distributed along the object, I can have a more accurate representation of the physics. Okay, so we have options. Okay, let's take a look at how we can, and I'll just write this here because it's sometimes a little confusing to say, oh, what is f of a plus da da da? Okay, we have options, ways to look at this, and you can think of f of x as being a value at the next location. Right? So what do I mean? I mean that in this framework, if I have an interest in knowing what's happening at this location here, I can use information about what is happening or what has happened, okay, or what will happen, what I know at the previous step to do this calculation. All right, so this may be a little bit confusing, but let me see if I can try to put it out there. Okay, so we can say that using the Taylor series expansion, the value that we're interested in for temperature at a location T of x sub I plus 1 is given by some value at A, where we say it was known. So that means that we knew this, okay? And plus the slope at this previous value, or this value here spatially before x of I plus 1, times the delta x, the difference, between x of I plus 1 and x of I, plus then doing this with the second derivative. And this is just Taylor series expansion. And we're going to then simplify things and say we can ignore these higher order terms. So now, if I want the value of temperature here, I can estimate it based on the value here plus the slope times the distance. This is just mx plus b, or b plus mx, if you will. Right? That's how we calculate that value at that location. That's you could call it extrapolation if you want, or you could call it interpolation. Interpolation is usually in between objects. Extrapolation is when you're going out. Okay? This is called a forward difference. Okay? Or a forward first difference. Okay? You see, we're figuring out where something is, or what the value of something is, based on values from the past. Or not the past. I'm still in time. Based on a value behind it. Okay? We're going to introduce time in a little bit. Right now, this is all spatial. Okay? So, the next thing, all right, is, well, what is the slope there? All right? Well, let's break this slope into another approximation, which we would say is going to be like that. Okay? So now what we're saying is this times that, all right? Just reorganize using the Taylor series expansion that we have to then figure out what the slope is at the location. Okay? So this is the forward difference. Okay? And it's truish, in a truer form, usually what we're looking at is this slope term. Okay. So this one would really be what you use. Forward difference and what we will use. Similarly, the backward difference can be, I'm skipping some of the math here, but you can write it out as the following. Can be approximated as that. Okay? So, when would you want to use the backward? Okay? well, let's say everything is awesome in the middle. I can go forward or backward. Okay? I can go forward or backward to figure out what the slope is at a given location. Okay? What does that mean? That means, okay, if I want to figure out what the slope is at x of I could use the value over here, and that would be forward, and the value here, and I can figure that out that way. Or I could go backward instead to try to approximate what it is here. I could use this value. What happens though when you're at the left end? Or what happens when you're at the right end? Yeah, go ahead, Josh.
You only have one option.
You only have one option, okay? Right? And you need both options to solve the entire problem, right? Because you have a left and a right. Left end and a right end, okay? So we have the opportunity when we code to keep track of these differences. Now, there's also a centered difference. Okay? So the centered difference makes use of forward and backward differences. Okay. So essentially what you do is you say, okay, I'm going to take dt x of I, and I would rewrite, this is the forward one, and I add it to the dt x of I dx of the backward, and this gives me 2 times my value. And this value that you have here, if you do centered difference, and I'm skipping some of the math, dictates that you will have the following expression. Like that. Okay? That was weird. Did it copied it down? Oh no. And I can't select it. Oh, what? Is it going to put that on every slide? Oh. Okay, hold on, folks. This one. Oops. Okay. Blast. It just lost stuff. Okay. So, anyway, so if you were recording that, the center difference is going to be t of x of I plus 1 minus t of x I minus 1 over 2 delta x. Okay? So this is another way for us to approximate the spatial derivative. And in this case, we're getting the derivative at a given location using the points on either side of it. Okay. Now, the second derivative, all right, can also be approximated by applying the Taylor series again. Okay? And you can add the forward and the backward terms with these second order terms to get these values. So in that case, the second ordered centered, okay, this expression looks like this. Why would we want a second derivative? Well, if we go back to the heat equation, right, what do we see? We see we have a second derivative with respect to the x. So by using finite difference a couple of times, we can come up with an approximation. This approximation allows us to calculate these derivatives, first and second derivatives, with a mesh, with a discrete number of elements. And we're doing finite differences. We're actually calculating these differences and accounting for them. Okay. So this portion right here is that second derivative, all right? This is the alpha in front of it, okay? And this is a first derivative of time, okay? But we can play a little bit of trick here. So what we're going to say is, hey, if I'm interested in a delta t, I'm going to say I have a delta t. Sorry, that's bad, right? If I'm interested in a change in temperature, I'm going to have a change in time, okay, times this k over rho c, okay, so I've just moved this over here, k over rho c, which I'm going to say is my alpha, and I have my second order differential equation, and if I go back and I use the centered difference right here, okay, I have that this can be written as t of x sub I plus 1 minus 2 times t of x I plus t of x minus 1 all over delta x squared. Okay. So this is the 1D heat equation in a finite difference form. Okay. When you code this up, this is not the way I learned finite difference when I was a grad student. Okay, but this is the John Singer way, which is beautiful. Okay, he likes this function called circ shift. Okay, and let me explain a little bit of what circ shift does. It applies the periodic boundary condition. Okay, you remember the periodic boundary condition where one thing goes out one wall and it comes back in the other wall? So if I have M is equal to A, B, C, D, E, F, G, H, I, like this. And then I apply a circ shift to the columns, all right? So I do circ shift of M, and I put in that I want to leave the rows alone, but I want to move the columns one to the left, okay? This will then give me B, C, A, E, F, D, H, G. Okay, do you see this? So all the columns, or all the values in the columns have moved one to the left. And if it was going to get kicked out of the matrix, it gets circled back to the other side. Now, why would Professor Singer think this is a good idea? Any ideas? Yes.
It could potentially help with looping functions if you continuously have the matrix shuffle and then just index the same spot.
Yeah, so essentially in the code, what you do, all right, this is the second difference right here in this line, okay? And what you can do is you can take two matrices or two arrays and you can subtract them from each other, and you've now calculated the finite differences at each of those locations, right? So if I took my M matrix and my search shift matrix right here, right? And I said, oh, I want to do M minus this search shift matrix. Then I've got, in the first row, first column, I've got A minus B. All right, in the second column, first row, I've got B minus C. And then the last one, I've got C minus A in the top right, okay? So this is a nice, clever way to essentially apply these finite differences quickly to matrices. Okay? All right. So the circ shift is a periodic boundary condition. Okay? When we apply, okay, so this is, let's do some examples, and we're running out of time. Hopefully we're having fun. Okay, or you're asleep, either one. I feel that you can give me credit for either being bored or asleep or having fun. All right, so here, what we have is a system that starts, whoops, did it stay? Yes, good. It starts with a gradient. Okay? And in this case, right, you see the gradient is 1 Kelvin per step in x position. And we're going to let this system run from these initial conditions. Remember, one of the things you can do with differential equations, you can solve the force result, or you can solve the response to initial conditions. And in this case, we're going to have it be periodic. Okay. So with the circ shift, we already saw that, right? The next time step, what's going to happen to this value? It's going to see the value over here. What's going to happen to this value? It's going to see the value over here. They're going to interact because this is periodic. And if this is a system that's trying to reach a thermal equilibrium, that means that these values over here are going to go up because this is higher than that, and these values over here are going to go down. And that also means that it's going to affect the neighbor, it's going to affect the neighbor, and it's going to just propagate, right? So what we see is exactly that, okay? As time progresses, as it marches in time, remember the heat equation has a time component to it as well, right? It has a dt, right? We said it was that delta t times the alpha times the central difference. Center difference. So this thing is marching along and running its calculations as you see here. Very quickly, the fastest I've ever covered boundary conditions. Okay. Everything is awesome in the middle. Okay? It's the boundaries that are a pain. Okay? And so, like we already said, you have to be careful. Maybe you have to do a forward or a backward difference depending on which side you're on. But real systems aren't necessarily just periodically saying, hey, the right should just affect the left and the left should affect the right. That's not how heat transfer, across a bar with the temperature provided on one side, temperature provided on another side works. It's just not. Okay? But we can still think about periodicity because we have that happening essentially, across the board along the element. So there are two boundary conditions that we want to really emphasize. And one is called a Dirichlet boundary condition. Okay? And so with Dirichlet, what it is that if you have a left and a right, or some element or something with length L, okay, and this is Dirichlet. My French is, well, kaput. All right, you can prescribe boundary conditions at those sides. This is the nicest boundary condition, in my opinion. Why? Because, yes, you have things going on inside. In fact, you have internal heat flux. I should have mentioned that. Remember, the Fourier's law says that a change in temperature over a length is a heat flux, right? And I forgot to mention that, okay? So internally, yes, what's happening, if you have one node with high temperature and one node next to it with lower temperature, it's the heat flux, the difference in that temperature, that's going to cause the one on the right to heat up a little bit and the one on this side. Anyway, you know what I'm saying. That's what's causing these changes, this heat flux between the elements or between the nodes. Okay? But here in Dirichlet business, the boundary conditions now make this problem actually simpler. You don't have to do the periodicity stuff. You just say, bam, that's your temperature. Left side, right side. Do not change that temperature. Is that realistic in real life? Well, if you have a really big lake next to whatever it is and that temperature doesn't change that much, okay, yeah, that's a good condition. But technically, right, the local temperature is going to be influenced by whatever you're sticking in that wood. Anyway. But this is a nice, realistic way to look at things. The Neumann boundary condition is harder. And what this boundary condition essentially says is, I can prescribe a heat flux, okay? And this we'll call this QL, okay? So this is the 0 side, this is the L side, okay? And in this case, you have a normal vector coming out this way, and in this case, you have a normal vector coming out that way, okay? And so the Neumann boundary condition on the left side, we can say that QL is, left side we say that the gradient in the temperature dotted with the normal vector, okay, is going to be given as some Q naught over K. So this is essentially Fourier's law, right? We said Q is equal to K times the gradient of T. Okay? So this is just a representation of Fourier's law, but we call this a Neumann boundary condition, and this is what heat flux is going in. So, maybe you've got like a stove on one side of this bar that's electrically powered. Okay, so you got some coils. And so that flux can be given by whatever the Q, so like, you know, electrical power is equal to current times voltage, I wanted to say velocity. P equals IV, right? So you could divide that by K, and that's the heat flux coming into that side of the bottle. Okay? And the same thing for the right side. So the right side would have a gradient in temperature dotted with an L, and this would be equal to the QL, and it's negative over K. So this is how we represent some of the inputs that you put into a system. Say, hey, I'm going to fix the temperature on the left and the right, or I'm going to fix the temperature on the left side and the right side. I'm going to say, I've got a torch, and I'm putting this heat flux on one side of my system, and I'm going to heat the whole thing up, all right? So I'm kind of out of time to go through some of the details here, but let me, you can look at the slides if you like from the previous year. That sounds lame, but it's there, okay? And when you do the actual coding, all right, you'll be able to see the code in action, all right? But let me just talk a little bit about how this gets implemented in 2D. You have a grid now and here what you're going to see in the code is that these circled regions on a grid are important. Well, not important. They are painful. Okay? What happens is you need to know if you're on the left side, but you're not. So if you're in the top corner, right, you have to apply whatever the temperature is that's set there. If you're on the left side, you have to apply whatever temperature has been specified on the left side. Top, right, bottom. These are kind of special regions that you have to keep track of. And when you do this with the Neumann boundary conditions, it's worse. The math gets worse. Okay? So, for example, here is a 2D implementation. So I kind of figured I want to use everything. Okay? But here, what you see, this is how you go about calculating the flux on the left side of your system. Okay? What you have to account for are fluxes from the neighboring, not particles, but nodes, okay, to calculate what's happening. And then you would have the heat flux coming from your outside environment hitting that particular node as well. And that heat flux comes in here, and then the interactions with temperature on those neighboring elements, they end up with this expression here. So the change in temperature, okay, at this left node is being affected by all its neighboring nodes plus what's coming in from the outside. And that's kind of the general theme. Any questions on this? All right. Hopefully you have a little bit of appreciation for what's happening with finite difference, okay? And eventually, what you get to do in the homework is think about a rectangular turkey or a square turkey, okay? So this is a simulation where we're saying, I want to see how the temperature at the middle of my turkey changes as a function of time based on Dirichlet boundary conditions. Okay? And I got to see, oh, after 10 minutes, it's this temperature in the middle. How long do I have to cook my turkey to get it to a healthy 165 degrees Fahrenheit? Okay? That's the type of problem we're going to be solving. Thank you for coming today and participating. And let me put up the attendance. Let me shut off the broadcast.